Hello students, it's Kailash. Lesson number 1, Electrostatics of 12th standard. And of course, in the video session, I deal panna pora topics 12th standard CBSE students ku ottu varum. So it's a common topic for both Samacheer as well as CBSE students of 12th standard. Samacheer students are the lesson number 1, electrostatics, and CBSE students are the lesson number 1, electric charges and fields. Okay, so in the video session, நான் என்னென்ன டீச் பண்ண போறேன். Firstly, I'll be teaching you what are macroscopic or large scale charges. Number 2, what are the two types of charge distribution. And number 3, why quantization of charges is ignored when dealing with macroscopic or large scale charges. Now first we shall see what do you mean by a macroscopic or large scale charges. So what do you mean by macroscopic charges or large-scale charges? Charges which are very large when compared with an electron charge are called macroscopic or large-scale charges. So ஒரு body carry பண்ற charge ஓட magnitude electron charge ஓட compare பண்ணோம்னா body carry பண்ற charge ரொம்ப huge value-ஆ இருக்கணும். Or in other words, if the charge of an electron is negligibly small when compared with the charge under consideration, that is charge on a body, then such charges are termed as large scale or macroscopic charges. So ஒரு body carry பண்ற charge ஓட magnitude ஓட electron charge ஓட magnitude compare பண்ணா the electron charge has to be negligible. So அப்படி இருந்தா then the charge carried by the body is said to be a macroscopic charge or charges in large scale. இதுக்கு ஒரு example பார்ப்போம். For example, order of charge of an electron. You know, order means I have to take only the power. You know, electron charge is 1.6 into 10 to the power minus 19 coulomb. So order of charge of an electron is 10 to the power minus 19 coulomb. Now let me compare the order of charge of an electron with 1 microcoulomb. So order of 1 microcoulomb of charge. You know, charge of an electron is taken as E and the charge carried by a body is taken as Q. So assume a body is carrying a charge of 1 microcoulomb. So order of 1 microcoulomb is 10 to the power minus 6 coulomb because micro means 10 to the power minus 6. Microcoulomb means 10 to the power minus 6 coulomb. So let us compare the charge carried by the body, which is in microcoulomb order, with the charge of an electron. You know, whenever you want to compare two quantities, you have to find the ratio of the two quantities, okay? So here I'm comparing the charge carried by the body with the charge of an electron. So I find the ratio of these two. So order of charge carried by the body is 10 to the power minus 6 and order of charge of an electron is 10 to the power minus 19. So on dividing these two, I will end up with 10 to the power 13. Just take 10 to the power minus 19 to the numerator. You will have 10 to the power minus 6 into 10 to the power plus 19, which will give us 10 to the power 13. So thus, the ratio of charge carried by the body to the charge of an electron works out to 10 to the power 13. Now on cross multiplying, taking e to the right hand side, I get charge carried by the body equals 10 to the power 13 times charge of an electron. So if you look at 1 microcoulomb of charge, it is found to be 10 to the power 13 times larger than charge of an electron. Or in other words, the electron charge becomes negligible when compared with charge Q on the body. So thus, I can say 1 microcoulomb charge to be a macroscopic or large-scale charge because when I compare 1 microcoulomb of charge with charge of an electron, the electron charge becomes negligible. So I hope you would have understood what are macroscopic or large-scale charges. Right. Now we'll go into the next slide. Distribution of charges on a body and its types. Distribution of charges means collecting the charges, collection of charges. So whenever I collect the charges on a body, then I say I am distributing the charges on the body, right? Now there are two types of charge distribution. Number 1, discrete charge distribution. And number 2, continuous charge distribution. So firstly, we shall see what is discrete charge distribution. Discrete charge distribution is the one in which we will be able to identify individual charges separately or distinctly, just like marbles or balls rolled on a floor. So you have few marbles in your hand. Assume that you are rolling it on a floor. After rolling it on the floor, you will be able to see each and every marble individually or separately. First marble, second marble, third marble, like that. You'll be able to identify them distinctly or separately. So whenever you are able to identify certain entity distinctly or separately, then we use the word called discrete. Okay. So discrete means distinct or separate. For example, let me consider a body. What I'm going to do is I'm going to distribute charges on the body like this. I'm distributing charges Q1, Q2, Q3, Q4, Q5, and Q6. And assume that these charges are getting focused on a very small region of a body, microscopic portion of a body. So the charges Q1, Q2, Q3 are focused on a very small region of the body. They occupy a very tiny region. They're far apart. So just like marbles or balls rolled on a floor, I'll be able to individually identify them. So here we have a charge Q1, here we have a charge Q2, here we have a charge whose magnitude is Q3, here we have a charge whose magnitude is Q4, and so on. So such charges which can be individually identified are called discrete charges. Okay. Now, what do you mean by continuous charge distribution? A continuous charge distribution is the one in which the charges are distributed or packed very close to each other, such that identifying individual charges becomes quite impossible. So the charges on a body are distributed in such a way that they are congested, they are tightly packed, they overlap with each other. In such case, the charges cannot be identified individually, as we saw in the earlier slide. So it will appear to be continuous, which is analogous to a straight line. You know, a straight line is composed of several dots which are closely packed with each other, isn't it? So just like that, charges, if they are tightly packed, they don't appear, we can't see individual charges. Rather, we will be seeing them in a form of a continuous pattern. For example, so these are all dots which are going to form a line. You can see that dots are distinctly seen. They are far apart. In such cases, I'll be able to identify each and every dot separately. So thus, these dots which are far apart are said to have discrete nature. Whereas, now you can see the dots are tightly packed. Packed. They are getting tightly packed. You can see I'm not able to identify individual dots because they are so close, they overlap with each other. And I'm not able to identify individual dots as in the earlier case. So thus, these dots are tightly packed so that I get a continuous structure in the form of a straight line. Likewise, let me consider a few positive charges are distributed on our body like this. The charges are far apart. In such case, I'm able to identify individual positive charges over here. So these charges have discrete nature. Now let me consider the positive charges are getting distributed on the body. You can see how tightly they are packed. They are closely packed. You are not able to, we cannot identify individual positive charges as in the earlier case. They are so tightly packed or close. You can see. Okay. Now these charges are tightly packed such that it appears as a continuous structure. So such type of distribution is called continuous charge distribution. So this is your discrete charge distribution, and this is continuous charge distribution. Okay. Now, why quantization of charges is ignored when dealing with macroscopic or large-scale charges? You know, as per law of quantization of charge, magnitude of charge carried by a body will always be available as certain discrete values, that is integral multiple of electronic charge. That is, a charge carried by a body will always be an integral multiple of charge of an electron, Q equals to N into E. But the above fact is applicable only in microscopic scale, wherein the charges have discrete nature. Discrete, whenever the charges has to be discrete, they have to occupy a very, very small negligible dimension of a body. If the charges occupy a very negligible dimension of the body, then at that particular region, the number of electrons lost or gained will be very, very small in number, maybe in few tens or few hundreds. But whereas in a macroscopic scale, the number of charges that are lost or gained, number of electrons that are lost or gained will be very, 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 very incredibly large. So in such cases, though macroscopic scale of charges obey law of quantization, since the number of electrons lost or gained is so large, I can ignore law of quantization of charges in such cases. So as per law of quantization of charges, magnitude of charges are always available as certain discrete values. That is integral multiple of charge carried by an electron, Q equals to NE. And this concept is applicable only for microscopic scale, that is for charges having discrete nature, and not in macroscopic scale where the charges have continuous distribution. Now this is the reason. So if they ask you why quantization of charges is ignored in macroscopic scale, you can write the answer, what I'm going to teach you now. In macroscopic scale of charges, the charge carried by a body will be very much larger when compared with charge of an electron, or in other words, the charges are so closely distributed that they appear to be continuous and not discrete. Hence, the number of electrons lost whenever the charges have continuous nature, continuous distribution. Whenever the charges have continuous distribution, the number of electrons lost or gained will be incredibly large. So though in continuous distribution, law of quantization of charges is obeyed, since the number of electrons lost or gained is so large in number, we can ignore it. So hence, quantization of charges can be ignored. So I hope you would have understood why quantization of charges is ignored in macroscopic scale. So that's all in this video session. Meet you in the next video session. Until then, it's Kailash signing off. Bye.